Let's see if we can use the same proof using the program Fitch. Okay, so here is the proof set up as a Fitch file. Our premises are for all x, tet x implies small x, and for all z, small z implies left of zb. We changed the bound variable here, but obviously that doesn't make very much difference. And our goal is to prove that every tetrahedron is to the left of b. So let's begin by taking the formula that we're trying to prove and adding it as our final step of our proof. So we now know that we're trying to prove for all x, tet x implies left of xb. Now remember we said we were going to do this by setting up a subproof and assuming tet c and trying to reach the formula left of cb. Now, we have to find a way to represent this boxed constant, the thing that tells us that c is supposed to be a new constant. And the device we use in Fitch is this little pull-down menu here, which enables us to select the constant symbols or other symbols from this little menu. So here we select c, and you can see that the c appears in the box just as if we were writing it on paper. So now we can check that this rule, if we could complete this proof, we would be able to use universal introduction to verify the conclusion that we're interested in, that every tet is to the left of b. And sure enough, this tells us that that this is a correctly constructed proof. And this is really the point of this demonstration, to show what a general conditional proof looks like when used in Fitch. We start a subproof. We select the constant, the box constant here, from using this little pull-down menu. Assume the antecedent of the instance of the antecedent of the implication that we're trying to prove, and add as a last line of the proof the consequent of that implication, the appropriate instantiation of the consequent. Everything else should be plain sailing. How are we going to prove this? Well, in our example proof, the first thing we did was we instantiated for all x, tet x implies small of x, and so that was a step of universal elimination, and we obtain tet c implies small c. And this, of course, is an instance of this general claim here, so this should check out. Now we can use implication elimination to give us our intermediate conclusion, namely that c is small. And this too, let's check that this is going to check out. Again, we're in good shape. Now we need to do the same trick again. We're going to instantiate the formula for all z, small z implies left of zb, with the instance c. So again, we need small c implies left of cb, and that's again obtained by universal elimination from this second premise now. And finally, we can derive the conclusion that we want to, again using modus ponens, implication elimination, on these two formulae that we have derived. And now every single step of our proof checks out, and the goal is proved.
Terrific. Hey Dave, let's try something here. What if we change that C to a B and tried to construct the same proof using B, even though B actually appears in the premises? And then we could prove that for all x, if x is a tet, then x is the same as x. X is to the left of x.
That would be bad if we could do that. So you're suggesting that we, instead of using the constant c here, we instead use the constant b.
And then we change the b's.
And then we change all of the c's to b's.
And then the conclusion is, for all x, if x is a tet, then x is to the left of x. So change that b to an x. Now, what's going to happen here? Let's check that proof out.
Let's check the proof out. And notice that the application of universal introduction fails here as we hoped it should. We hoped that something was going to fail, and none of these universal elimination or implication elimination steps were going to fail. So this is where we expect things to go wrong. And the reason it fails is that a name has been introduced as new, which was already in use. And B was claimed here to be a new constant, but it was already in use in the proof up here. And so it could not be exported out. It could not be treated as a brand new variable.
Phew, that's a good thing. Okay, so there's some neat shortcuts that are built into the various rules in Fitch, and so let's look at these cases. First, the default cases. If you don't enter a formula that you're trying to infer when using universal elimination, then Fitch is going to construct an instantiation for you. It's going to put a particular constant in for the variable.
So suppose that we were being lazy, and instead of entering this formula here, we just said to Fitch, we want you to find me an instantiation of this formula here. So if I check this step, Fitch will fill in the step for me, and notice it chooses the instance that we want. In this case, tet c implies small c.
It read our minds.
It read our minds. Well, actually, it's a little less smart than that, but it's pretty smart. What it does is it uses the box constant at the beginning of the subproof that we're in. And if we're not in a subproof, it uses the alphabetically first constant that's in use in the proof. So, but the point remains that if we do not enter a formula and tell Fitch to find us an instantiation, it will generate an instance for us, and it will often get exactly the instance that we need to take the next step in the proof.
So that's pretty cool. Now, if you don't like the instance that Fitch has found, you can actually specify a specific instance. So suppose, for example, here, that for some reason we didn't want to use, in this case, we didn't want to use C, but we wanted to use D.
Okay, so we can tell Fitch what instance to create for us by giving it what we call a substitution, and a substitution is signaled by the use of a colon followed by the variable name that we want to instantiate, in this case Z, followed by an arrow, a greater than sign, which is intended to indicate we want to replace Z by something, and then this is the something that we want to replace it by, D. So this substitution here says, make me an instance of the formula that I'm citing by replacing Z with the constant symbol D. And when we check this step, lo and behold, Fitch does that for us, and it records the substitution that we used at this step.
That's pretty cool. So now if you're using universal introduction, then Fitch will generalize over the box constant in the subproof, as Dave already demonstrated. And that ensures that either general conditional proof or universal introduction is correctly constructed. But if you don't want that box constant, or you want some other variable, then you can do that by specifying the variable that you want in the way that Dave showed. Or alternatively, you can simply have it instantiate with the variable it chooses. If it chooses the wrong variable, then the wrong constant, then you can go and replace that constant. Just edit the formula.
So notice that if we do not enter a formula in this last step of this proof, where we're using generalized conditional proof, Fitch has all the information it needs to determine what formula should go in here. It can see that we're using general conditional proof because there is an assumption formula at the step here. We know it knows what variable, what constant symbol to generalize over, and so again, when we check this proof, Fitch will fill in the formula that we need that this subproof demonstrates. So Fitch also has generous uses of the rules. So when using universal elimination on a formula that has multiple universal quantifiers, you can remove them all in one step. So for example, if I have the formula for all x, for all y, for all z, between x, y, z, I'm allowed to infer between a, b, c from this formula using universal elimination in a single step.
So Dave, suppose you wanted Fitch to fill in the constants for you, and you didn't want to type out the formula. So this is a pretty short formula, but suppose you had a long formula. Can you do that?
So if you're just suggesting that I leave this blank, then,
Right.
then when I check the step, Fitch doesn't know how many quantifiers that I want to eliminate. So it will in fact give me the single with one quantifier eliminated. And again, and now because we're not in the context of a subproof with a named constant, it's going to use the alphabetically first available constant to be the instance.
But what if you wanted to tell it? Use A, B, and C for X, Y, and Z.
Okay, and here we can generalize the idea that we had before by providing a substitution. So we can say, for example, for X, put F, for Y, put B, and for Z, put A. And when we check this formula out, we'll get between F, B, A, and it records again as a comment the substitution that we use to help the reader understand how we obtained this instance from the general formula.
Great, great.
Okay, and there's one more thing that we can do, and that is we can prove a formula with multiple universal quantifiers. So suppose I have for all X, for all Y, for all Z, tet X implies between X, Y, Z. So again, I want to use general conditional proof to complete this proof. So I might start a subproof, and here I can use three box constants all in one subproof. I'm saying let A, B, and C be arbitrary objects, and my assumption here is going to be tet A, because that's the first, that's going to be my antecedent. And in this proof, if I can prove between A, B, C, I can do that using universal introduction, citing this subproof. Unfortunately, A and B and C have already been used in this proof up here, and I think I have no constants left that I could use. But the principle should be clear. If I'm trying to prove a universally quantified formula, and I'm going to do it using universal introduction, I need new objects for each of the universal quantifiers. I can eliminate them all at once, rather than be forced to eliminate them one at a time and have an increasing depth of nesting of subproofs inside my proof.
The add support steps feature can also be used with both of our rules. In the case of universal elimination, Fitch will construct a universal formula with the leftmost constant generalized. In the case of universal introduction, the add support steps function adds the appropriate subproof with multiple box constants if necessary, and with the appropriate assumption if the matrix is of the conclusion is an implication.
So let's see that in action. Suppose I have the formula between A, B, C, and I tell Fitch that I want to infer this by universal elimination. So, and I ask Fitch to add the support steps. What things would I need to know in order to be able to do this? And Fitch correctly enters for all X between X, B, C, generalizing the first occurring, constant in this formula. Similarly, if I ask to try to prove for all X, tet X implies cube X, something that would be very difficult to prove, and I tell Fitch that I'm going to prove this by universal introduction. When I add support steps to this for this inference, Fitch will create for me a subproof with a new constant. It chooses C0, just invents one that it knows is not in use, and makes the assumption tet C0 and asks me to prove cube C0, and now I have the obligation to fill in this proof. So it's easier than thinking. Now we can turn our attention to the rules for dealing with existential quantifiers.